Hello, we are SmoothRide, AI pothole detection. I am Nicholas Gray. I was on the AI team and I was one of the co-project leads, the Scrum Master, the head of the AI team, and also in charge of the laptop program development.
Hi, my name is Thomas Walsmith. I helped collect data for the initial version of the AI model and designed and implemented the API and database.
I'm Kyle Williams. I was in charge of training the AI model, database development, and creating the actual database.
I'm Mason Williams. I was the other co-project lead. I handled a bit of infrastructure and administration, as well as being a part of the mobile design and web application development.
I am Andrew. I did the mobile app development and I did the AI to app integration.
Hi, I'm Aaron. I started off working in mobile and then moved to working on the database as well as the web front end and deployment.
So, what's the issue with potholes? Potholes have cost over $3 billion per year in vehicle damages, over 34 million pothole damage claims per year. 15% of drivers have reported damage from potholes in the last 5 years. 19 states will not reimburse for any bodily injuries, and 9 states will not reimburse for any property damage or bodily injuries caused by road damage. So this is an issue, but what's the solution? Our solution is SmoothRide, which uses the power of AI to help drivers know where potholes are coming and to avoid them, and to help municipalities know where potholes are so that they can fix them later and make our roads safer.
When you're creating an AI pothole detection app, the first thing you need to do is create the actual AI model. And to do that, you need a large data set of images to train it on. This is our data set. It has 9,303 images and is hosted on RoboFlow, which is one of the most popular dataset storing programs to use. Every single one of these images has a pothole in it, and that pothole is identified by a bounding box. This is so the AI model actually knows where to look for when it's trying to find what is a pothole and what isn't a pothole. Now, on this data set, we trained a lot of different models. We trained big ones, we trained small ones, but the final best model that we had was a YOLO V8 model that you can see right here. It has 100 different epochs, which means it was trained over 100 generations. And the final result is that it had a 0.656 map 50 and 0.315 map 50, 95, which are both tests of how precise the AI model is at actually detecting the potholes in the image. Now, this was our best model to use for the computer program, but we trained a much smaller one for the mobile app, and that was part of the reason that we moved on from the mobile app to use the laptop program. Andy will talk about the failed mobile app right now and what went wrong and what we learned from.
This is our final mobile application design. We built the app in Flutter so that it can run on both iOS and Android devices. We also decided to use Flutter because it has many libraries to support running a machine learning model. In this example, you can see we have a model integrated within the app already using the TF-Lite libraries. When a pothole is detected, we use the geolocator library to send the user's location to the database. The screenshot shows that the road overlay that should help the user align the camera with the road. It also shows the alerts, which show up on either side of the screen depending if the pothole is on the left side or on the right side of the screen. The other screenshot shows the settings page that allows changing the settings throughout this application. So these are the final results of the app. As you can see, there is a few inconsistencies. Sometimes it would show false positives. It would detect some false positives, and the warning banners would sometimes show up. So we were not too happy about it. So we decided to go another route.
Thank you, Andy. I will now demonstrate the full capabilities of our laptop program. The first step is to set up the lane detection. The lane detection allows the user to tell the program where the lane that we are driving actually is and to where to actually look for the potholes. This helps us to prevent bad potholes from being detected and from making it into the data set itself. So while I'm driving here, I'm adjusting the lane so it'll fit exactly to our road. And once we have that, we can actually turn on our pothole detection. And now to just keep the live updating, you don't have to keep the lane setting on or off. You can easily turn it off here and it will still operate. It will just be invisible. But for now, I will keep it on. As you can see, as we're driving around, we are missing any false potholes and we haven't any detected yet. That's because of our robust system. You also have ability to change some settings about the detection. For example, you can adjust the confidence of the model, which is how confident it is to detect a pothole. You can control whether we display a pothole. You can also change which model you're using. You can also control the alerts, which is with the system of whether we actually detect a pothole or not. And you can control how opaque it is, the delay of it, and the width. And then finally, you can actually change whether we're showing video feed, showing the lane detection, or changing the camera. Now, as you just saw there, we just had an alert. And what it does is that as the potholes are as we're watching, if we actually detect a pothole, it sends an alert up to the database, which actually logs where the pothole is and its geolocation. And if there's an image present, we'll log it there. The pothole detection system also will actually try and predict if the pothole is on the left side or the right side of the lane based on looking at where the center of the bounding box of the pothole appears. And if it's on the left side of the lane, a left alert will play, and then if it's on the right, a right alert will play. And this alert will actually have a delay on it before being able to create another one, just to make sure that we don't accidentally ping the database multiple times with multiple duplicate potholes. Now, once we've collected all of our potholes, we can actually go to the pothole viewing map. Now, to do a quick refresh, we can actually see every pothole that has ever been plotted and collected by the database. And with each pothole, we can actually also view a picture of it if there's an applicable one. Like for example, here, we actually can see the pothole in this picture. And you can also have the ability to add and delete potholes from the database right through the map. For example, let's say we knew a pothole was right here. We can easily add one, and then like, oh wait, this is not actually a real pothole. We can easily delete it from the database. Now, let's say you want to download a certain set of potholes. For example, what if I'm interested in these three? It's easy as selecting a bounding box around the potholes, then clicking Generate Report to generate a report of them. And once that's generated, it just takes a couple seconds to make it. And as you can see, the selected potholes show its latitude, longitude, and the address of the pothole. And if you wanted to try and get every pothole in the database, you just have to have nothing selected, and you generate the entire report. As you see, every pothole in the database has been collected and the address given.
Alrighty, this is our website. As you can see, it does feature that Google Maps plugin. And as I zoom in here, bear with me, my computer is a little slow. You can see all the potholes we've recorded on our demos. And let's say I'd like to get an export of this, so I can view all these in a CSV with their respective locations. I'll just click this button right here. And then I'm allowed to download the CSV file. And once it is downloaded, I can open it. And then these are all the potholes that were viewed in frame with their ID, coordinates, and the number of times they have been reported.
Now, when it comes to our database, it's actually fairly simple. We are storing the location of the pothole, how many reports it's received, the first and last time it was reported, along with the expiration date. So this expiration date is made 6 months after the last time it was reported, in case the pothole has gotten repaired or we need to just remove it from the database. There is a delta in place at 150 meters as well to avoid slight discrepancies in the user's location when the alert is made. And finally, in terms of potholes, we do have 3 endpoints: post, which given a location will either create or increment a previously alerted pothole; get would be given a location, it will return all of the potholes within a bounding box; and delete will remove a pothole from the database.
In terms of the web API itself, it's a pretty standard JSON REST API, and it exists to allow a number of advanced functionalities for us in the app, mainly the reporting of potholes and merging these reports in a database, retrieval of all these reported potholes within some given area, and storing images of those potholes and retrieving them as well. In terms of the actual web API itself, we have Express.js for the actual web API framework, TypeScript for type checking, and Bun, which is actually a drop-in node/npm replacement that offers out-of-the-box TypeScript support, which was really great for us as we were a TypeScript web API. Not having a build step during development was extremely helpful.
Thank you for your time.